The following program is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.
Hello and welcome back to Element 14 Presents. I'm Andy, and in today's episode, we'll be building a Game Boy wireless link adapter. A wireless Game Boy link adapter? Anyway, we're going to make a Wi-Fi module that allows us to play wireless multiplayer games on the classic Game Boy handheld. This year marks the 30th anniversary of the original Game Boy. The system was incredibly successful, and over its lifetime it sold nearly 120 million units. One popular accessory you could get was the link cable, which connected two Game Boys together via their serial ports. The way it worked was if you had a Game Boy and your friend had a Game Boy, and you each had a copy of the same link-enabled game, you could hook up this cable and play against each other. The problem was, of course, that you were tethered to your friend via the cable. So I thought it might be cool in honor of the Game Boy's 30th birthday to give it the gift of Wi-Fi. Let's get started.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
Let's quickly go over what we're going to build in this episode. So you can see here we've got two Game Boys, and for each one we're going to make a microcontroller-powered module that plugs into the serial port. These units will also have Wi-Fi built in, and rather than talk directly with each other, we're going to have a server with game logic, and these boxes will communicate wirelessly with the server. Now this is going to be a fairly code-heavy build. Our microcontrollers will most likely be programmed with C or C++, then our web server will be C#, mainly because I'm a .NET developer in real life. And finally we're going to have a programmable game cartridge, and for that we're going to write a whole bunch of assembly language. And when we combine all this together, we should have a game that can be played by two people over Wi-Fi. Our project makes use of Game Boy serial communication, so let's figure out how that works. Here's a diagram showing the pinouts of the link cable. There are only 4 wires, data in and out, clock, and ground. Inside the cable, the data lines are crossed, so data in on one Game Boy connects to data out on the other. It's important to keep this in mind because if you're identifying the wires by color, the two ends of the cable are not the same. Alright, let's take a look at the cable in action. I want to view the signals with an oscilloscope, but I don't have anywhere to attach the probes. So I'll cut the cable in half, which I need to do later anyway, and then I'll just throw some wires on a breadboard and hook up the probes that way. Today we're testing Dr. Mario because it's easy to get into 2-player mode and play a quick game. So here you can see the 2 data lines and the clock. Here are 8 clock pulses that make up 1 byte of data. And what's interesting is that for each clock pulse there can be changes on both data lines. And that means that communication happens simultaneously in both directions rather than like a back and forth conversation. There's only 1 clock line, so before any communication takes place, the consoles negotiate to determine which will be the master and drive the clock, and which will be the slave and use the master's clock to stay in sync. Beyond that, there's no real protocol to dictate how the data stream is supposed to look. Now it's time to design our link to Wi-Fi circuit. Ideally, we want a microcontroller with built-in wireless and a few available GPIO pins, and it should be as small and energy efficient as possible. I found a device that satisfies all these requirements, and that is the Arduino MKR Wi-Fi 1010. Now keep in mind that we need 2 of these, 1 for each Game Boy. Our project needs to be portable, which means powering it with a battery, and one unexpected feature of the MKR is that you can plug in a battery directly. It even has charging capability on the board. Unfortunately, we can't use it because the Game Boy uses 5-volt signaling, and the 5-volt pin, which we need, is only active when powering via USB. Unlike most Arduinos, this one runs at 3.3 volts. Since it's not 5-volt tolerant, we're also going to need a level shifter, and I found the perfect one for the job. To actually deliver power to the board, we're using a PowerBoost 1000C, which not only provides 5 volts to the Arduino and the level shifter, but also allows us to connect a physical on-off switch. We don't need the power supply quite yet, because during our development process, we're going to be programming the Arduino through USB, and that also gives us power. So we'll take our breadboard, and the beauty of the Arduino is that it's ready to plug right in. Now we'll solder on some pin headers to our level shifter like so. And then we'll take 1 pre-cut link cable, and you can see we've soldered on some jumper wires with matching colors so we can plug this into the breadboard as well. Now we just need some additional wires to tie everything together. And there you have it! Time to start programming. There are 2 parts to establishing communication between the Arduino and the Game Boy. We'll do the Arduino side first. Fire up the IDE and follow the instructions on the Arduino website to install necessary drivers. Our test will involve sending alternating byte values to the Game Boy. will display the received values on the Game Boy screen. A 0 bit will be represented by an empty square, and a 1 will be a filled square. At the top of our main file, we've got 3 constants, one for each pin that's connected to the link cable. To simplify matters, the clock will always be configured as an output. By always making the Arduino the master, we eliminate complicated negotiation code on both ends. In theory, we can also achieve higher speeds this way, but we're going to stick to the normal 1 kilobyte per second speed for now. In our main loop, we send an alternating bit pattern, wait 1 second, and then send all low values. Wait another second and then repeat. To output a single bit, we write out the bit value and set clock low, wait 60 microseconds, then set clock high and another 60 microseconds before the next bit. And that's it. Time to move on to the Game Boy side. Now the Game Boy is designed to run commercial games off of read-only cartridges, so you might be wondering how it is that we can program it. The secret is a special programmable cartridge like this. These are especially handy because they take a common microSD card. Put your ROM binaries on there and you're good to go. For development, we'll be using RGBDS, which consists of an assembler, linker, and graphics converter. That's right, the Game Boy is programmed entirely in assembly language. It might sound crazy today, but that's just the way things were done back then. And here's what Game Boy code looks like. I'm far from an assembly language expert, but it does work and that's what's important. There is a bunch of setup here, clearing the screen, loading graphics, and setting palettes, but the interesting bit is here at the bottom. This is the serial interrupt handler that gets called whenever data arrives on the serial port. And what we're doing is storing that 1 byte of incoming data into a variable that we call serial buffer in. Now, if we hop over to the VBlank interrupt handler called draw, which is where we handle our graphics, we read that serial buffer. Depending on whether a particular bit is set or cleared, we write different values to the background tile map, which has the effect of showing an empty or solid square. Building our code is dead simple. We're not even using makefiles, just a tiny batch file that prepares our graphics, runs the assembler and linker, and fixes up the ROM with proper checksums and whatever else it needs to work correctly on real hardware. Okay, now comes the exciting part. We save the new GB ROM file to the SD card. Pop it into the cartridge and load it up. And let's plug our breadboard circuit into the Game Boy and see if we don't blow something up. Is that cool or what? We're controlling a Game Boy display from an Arduino through the link cable. That is awesome. So I do want to briefly mention the screen here, because some of you may be thinking that this doesn't look anything like what you remember from back when you owned a Game Boy. And you'd be correct. For the purpose of this video, I modified the screens with backlight and contrast mods. You can see here a comparison of the modified versus non-modified screens, and the results speak for themselves. I highly recommend mods like this if you're thinking of playing Game Boy games today on original hardware. It's time to set up communication between the Arduino and a game server, and much like before, this is done in 2 parts. This time we'll start with a game server. We're using Visual Studio and we're going to make this an ASP.NET Core web application. And for the sake of simplicity, we're going to hard code a couple of things and make a few assumptions that are fine for this project, which you wouldn't normally do in a production quality system. The first thing is that I've configured this machine with a static IP address, so the client always knows how to find it without messing around with DNS. And then I added a binding with the IP address in the application host.config. I've also added an inbound firewall rule that allows TCP on the port found in the config file, and I've made sure to run Visual Studio as an administrator. Failure to do any of these things may cause errors. Here we've got a simple one-line method that just echoes back whatever you pass in. We'll call this endpoint from the Arduino to test it out. So we'll go back to the Arduino IDE and see if we can get Wi-Fi working. We'll install the Wi-Fi Nina library, which we'll be using extensively. Now we'll create a new sketch with this code. You can see our server IP in there, as well as the call to our say something endpoint with the text hello world. We need to enter our Wi-Fi credentials into the Arduino secrets file before uploading the sketch. After the upload, we open the serial monitor. We can see the Arduino connect to the network, call our game server API endpoint, and print out the return value. Looks good. Now we have a prototype device that can send and receive data to both the Game Boy console and our web application. Alright, I have a confession to make. When I originally thought about doing this build, I'd hoped I'd be able to find a way to make it compatible with all the Game Boy's original library of games. But I quickly ran into trouble. Your typical Wi-Fi network has plenty of bandwidth, but it's not real time. You'd need sub-millisecond latency to reliably handle most games. And I thought of several possible workarounds, but they all had problems. In the end, I realized that the only way to get a stable wireless link was to code a game from scratch. And although it's a lot more effort than I originally anticipated, we're not afraid of a challenge, so let's make this thing work. Our time's limited, so we're going to make this as easy on ourselves as possible and remake an old classic board game called Reversi. The rules, the graphics, and everything else about it are simple, and we don't have to worry about intellectual property issues because the game was invented well over 100 years ago. Very quickly, here's the actual board game itself. And this is a game in progress, and we've got these discs which are black on one side and white on the other. And players are assigned a color. So let's say it's my turn and I've got black. I want to place a new disc such that my opponent's discs are sandwiched in between, and then flip those over and make them mine. And the objective is, at the end of the game, to have more of my discs on the board than my opponent has of theirs. So writing a complete game in assembly language is fairly crazy, but it really gives you an appreciation for what it was like programming for older consoles. Let's take a look at a few of the highlights in our code. These game state constants reveal that the core of our game is basically a state machine. We have a game state variable that's assigned one of these values to track whether players are joining, whose turn it is, whether an animation is playing, and so on. And these constants define the actual byte values that we'll write to and read from the serial port. They need to be exactly mirrored in the Arduino code so that the two can communicate properly. The state of our game board is represented in an array of 64 bytes, which means we can identify a specific square in a very compact form. But it also means that we have to convert between the array index and XY coordinates in several places. And since there's no multiplication, division, or modulus instructions, we need to get creative with bit shifting. I've put all the tile images into a single PNG file, and you can see all the graphics for the game right here. We've got animation frames for flipping the discs, as well as a pixelized font for on-screen messages. And while this hand pointer looks gray, we adjust the palette in-game to make it look white. And this is done because white usually appears as transparent, and we didn't want the hand to be see-through. One thing you won't find anywhere in the client code is game logic. This is one major benefit to making a server-based game. Writing the hard parts at a higher level language makes things much easier. Here's some of the server code that scans the board to see if the current move is valid. I'd hate to have to write this in assembly language. The other major responsibility of the server is to track players joining and leaving the game. The Arduino code sits in the middle and coordinates messaging between the Game Boys and the server, and the amount of code here is small in relative terms. There was one unexpected challenge when writing this which has to do with HTTP, and that is that I had to parse it manually. I'm sure somebody has an HTTP parser library out there, but I couldn't find one quickly, so I just wrote my own. And this is not great code, but again, it works. In our main loop, which runs every 50 milliseconds, we ping the Game Boy for status. Depending on what we get back, there are a number of possible actions we can take, like calling a server API, for example. Now there's something interesting at the top of the INO file, and that's these two defines. Debug controls serial debug output, and don't define this unless you've got the serial monitor running, because otherwise it won't work right. The other one is the Game Boy ID. I chose 0 for one Game Boy and 1 for the other, but any two integers should work. And what we're doing here is hard-coding the identity of the Game Boy into the Arduino code. This may not qualify as a best practice, but it makes our lives easier for this project. Alright, that's enough code. Let's do a quick smoke test. You can see the messages at the top of the screen telling us whose turn it is, and that means all of our components are working together. Now let's figure out how to strap this circuit onto a Game Boy. Well, it works, but it's not really portable in this form. I mean, there's no sense in making a wireless device that needs to be plugged in for power. So I'm going to take what's on the breadboard and move it over to a perf board along with our power supply and battery. And we'll also add a power switch while we're at it. There you go, 2 identical boards. Now we know the dimensions we need to design a 3D printed enclosure. Here we are in Blender. The case is in 2 parts and will be joined with normal wood screws. I put a sort of rectangular strap on the lid, and that's where the Game Boy will go. Time to get printing. Now, even though these consoles are next to each other, they're not physically connected in any way. Everything here is wireless. I'm going to demonstrate by pressing the button to complete the turn on this one, and both screens should update. Here we go. Nice, it works. We have wireless Game Boys. That's all we have for today. Have you ever tried to add modern features to an older piece of technology? How did you make it work? Let us know on the Element 14 community at element14.com/presents. And we'll see you next time.